in 3 dimensions, and we have in mind for simplicity a spherically symmetric potential. E of r is only a function of the radial coordinate, not a function of theta and phi. This is of course the result of going to center of mass frame in two-body scattering. Yeah, it's clear. Considering scattering of two bodies, but if you go to the center of mass frame, it's as though there's one body scattering with a fixed potential. Yeah, so we formulate everything as a one body problem, a fixed potential. So this is our potential, and you could have particles coming from somewhere, in many places also. So this is the incoming wave, and then you expect an outgoing wave that could go in several directions. So this is called the forward scattering direction. This side, if there is anything coming here, will be called back scattering. It's a reasonable term. And this would be wide angle scattering. Yeah. And we are going to set up a coordinate system where this direction will be Z. This angle is going to be theta. Theta is called by a fancy name. Sorry? So it's called starts with P. Theta is called the polar angle. Am I right? Polar angle. This is spherical coordinates called polar angle. Then there is a third angle, which is this way. This way angle. That's called phi. And the fancy name for phi is azimuthal angle. So this will be our coordinate system, and for simplicity, we will imagine the incoming particles are coming from z equal to minus infinity. Since the potential is spherically symmetric, it doesn't matter where we send them in from. If we are sending only one wave from one direction, we can call that direction minus z. Of course, we could imagine sending things from many places simultaneously, but for simplicity, we will consider this problem. Of course, this is true only because it is spherically symmetric. If this potential is not spherically symmetric, incoming wave from here and there do not result in the same scattering. After all, if it is some crazy shaped potential, scattering from this side and that side are clearly going to result in different scattering cross sections. So we are focusing on spherically symmetric potentials. So for non-spherically symmetric potentials, does matter where you come from. So, okay. Now, just to make a remark about the S matrix, which we have been studying this morning, and this question was already asked. In this case, we are going to have an incoming wave from here. That's one possibility. But just like this morning, we could have an incoming wave from the left or from the right. These were the two standard scattering problems. Here there are many standard scattering problems. It could come from the left, it could come from there. Okay. So So the incoming wave vector K, yeah, that's of course going to be given by wave number of the incoming wave times some unit vector, inward directed unit vector. So N is a inward directed unit vector and K is the wave number. That is simply square root of 2me upon h bar square, like we had this morning. That's the incoming wave number. This is the incoming wave vector. Here I am not assuming spherical symmetry or anything. Different directions can all be considered. So the incoming amplitudes previously they were simply A and B. But now we need infinitely many of them labeled by different incoming directions. So you will have some N1 hat, N2 hat, N3 hat, etc. Okay, these are all the possible incoming wave directions. Each of this is an incoming vector. How will you parameterize these? Here you parameterize by 1 and 2, left, right. What are the parameters needed to parameterize these? Theta and phi. Because if you specify theta and phi, at that theta and phi there is an inward directed vector fixed uniquely. So there are as many as there are theta and phi. Okay, so one incoming direction for each point on the sphere. So you can send a plane wave in that direction n hat for any choice of n hat. These are all the basis of incoming states. So n hat for all unit vectors on sphere label the basis of incoming states. Now you will have a scattered wave also. You pick any one of these, it will result in a scattered wave. Right? See, for simplicity, you think of the incoming wave as a plane wave. Even though it may be coming from some strange direction, it is still a plane wave in that direction. That is, the wave vector may be like this, but the wave front will be like this. It's coming from here, wave vector is that way, the wave fronts are like this. So it's a plane wave. Incoming wave is a plane wave. So, incoming wave is a plane wave with wave vector k n hat. However, the outgoing wave is more complicated. Even if you send in a plane wave, what comes out is not a plane wave. This is where three-dimensional scattering differs substantially from one-dimensional scattering. Because one-dimensional, if you send a plane wave on the left, eventually you get a plane wave on the right. So the scattered wave has to be looked at more carefully. So roughly the scattered wave will go in all directions, a little in every direction. So roughly expect size scattered to be what kind of wave? Spherical wave. That's not a bad idea. To be a spherical wave. What do you mean by spherical wave?
Amplitude differs.
Sorry?
amplitude decreases.
Amplitude decreases as you go away. That is a good feature of a plane wave, sorry, of a spherical wave, true. But
Starting from a point, wave from a point.
Starts from a point. Yeah, okay, that's also, it has a point, yeah, that's right. But no, what's a plane wave? Let's go back there. Wave fronts are planes. That's what a plane wave is. A plane wave is one whose points of common phase are planes. So what is a spherical wave? Points whose phase is constant is a sphere. Spherical wave is one whose wave fronts are concentric spheres. That means the wave amplitude should only depend on R. That is psi scattered from spherical wave should be some function only of R. Because then if you put it equal to constant, it will fix some R. That is not a function of theta and phi. That's what a spherical wave is. More precisely, to take a simple example, basically a function of R is a spherical wave. But to be a scattered wave, it needs to be something else also.
Its amplitude should decrease.
Amplitude should decrease, but before that, see, when we talked about one-dimensional scattering, you wanted the wave to, transmitted wave to go rightward. You wanted the reflected wave to go leftward. Only then you call it a scattered wave, right? So what's the analogous statement here? Yeah, it must be outward direct, not inward direct. Explosion, not implosion. So scatter, yeah, should be an outgoing. When I say outgoing, I mean radially outgoing wave.
Why do you make an assumption spherical?
No, we don't even want to make that assumption. That's why these words roughly expect. Okay. So that's not really true.
The motivation for mathematics is not.
No. Reason is very simple. I ask a question, I get a half answer from first bench, I am considering that answer. Nothing more than that. We are considering what a spherical wave is. We will see what the meaning of the spherical wave in the context of scattered wave. I am not saying the scattered wave is a spherical wave. I am just saying, since somebody suggested, let's consider it.
Sir, but in textbooks, normally you will consider spherical wave. Why not cylindrical wave and some other wave?
Yeah.
So, that is the reason.
Answer is very simple. Person in first has suggested. That's all. No, I will answer the question. Just give me.
The center of
The scattering center. Okay. So you have a spherically symmetric scattering center. Yeah. So the spherical wave would, the wave fronts would be concentric spheres centered at the point of symmetry of that potential.
So instead, if it was something like a road,
yeah,
you would select this cylindrical coordinates.
Yes, that might be better. Sure. If the scattering center is not a spherically symmetric potential, some other kind of wave may be relevant. Indeed. In fact, we're going to see that spherical waves are not the right one at all, even for spherically symmetric potentials. It is not a spherical wave. It has to be modified. But it's not a bad place to begin. Yeah. After all, it's pretty obvious. If you send something from the left, why would you expect the things that come backwards and forwards to be the same? If you have a scattering center here, like a heavy block, then everything is going to come back. If you send it straight, zero impact parameter, nothing is going to go forward. Such a wave is not a spherical wave. So, this is just an initial discussion. Yeah. So so this is very roughly expect to be a spherical wave. Let's just discuss what a spherical wave is first. So Now, but it should be outgoing. That much we have to agree upon. So let us give an example of such a spherical wave. Can you suggest like for a plane wave that is rightward directed, you said e to the ikx. What's the analogous statement here? Yeah, e to the power ikr. Yeah, where r is the radial coordinate. Such a wave is outward directed because the time dependence will be e to the minus I omega t. So if I combine these two, it is kr minus omega t. If I put that equal to constant, it will tell me, okay, but the points of constant phase are those where r is equal to omega t upon k. There can be some additive constant also. Okay, but it just says that as time grows, r also grows. Okay, so think of it that way. Now, okay, so this is an outward directed wave. We will also compute its probability current and see that the probability current is radially directed. But some people also suggested that the amplitude should decrease as you go away. So, okay, because they have suggested we can even put an r here. Now, why put r here and not r squared? Not clear. You can put whatever you like. But no, there is a good reason for r. We will see. Yeah. So this is an example of a spherical wave. But as we just said, sorry? Correct. In this wave, as we have written, it has some trouble at r equal to 0. The question is, where is this valid at all? It is certainly not valid inside the scattering center. It cannot be because it has diverged. So, at best, maybe this is valid outside or something like that. We have to see. Yeah, so this can't be valid everywhere. So, not at r equal to 0. In fact, in order to understand the scattering, like we did previously, we need the asymptotic behaviors at minus infinity and plus infinity. If we relate them, we will know the S matrix and such things. We don't necessarily need the wave function deep inside, though we would like to find that also. But for many purposes, we need only the asymptotic behavior of the wave function. So certainly for large R, this may not be a bad first case. Indeed. So detectors are kept far away. So what they detect are essentially free particles, maybe spherical waves. See, you know that any spherical wave far away looks like a plane wave because the wavefront becomes almost plane. Okay, so now let's modify this a little bit. This can't be the full story because as we were saying, even for a spherically symmetric potential, we don't expect, see suppose you have some weak potential here, then you would expect if you have relatively high energies, most of the particles would go through, you might think. Some may be backscattered. Yeah. So, but there should be some angular dependence. Okay. So, for scattering from left, expect psi scattered to have an angular dependence. Yeah. At present, this is just a guess. Okay, we have to actually solve the equation to find what's appropriate. Yeah. So it expects to have some angular dependence. So we might expect that psi scattered will have some dependence on theta and phi times some e to the ikr, perhaps by r, I don't know. Okay. This brings in the angular dependence. But tell me a little bit, okay, there may be some constant in front also. If this is spherically symmetric, this F will have some special property. What is that?
It also not dependently to theta also. Around the given theta will be same.
Right. See, these are different thetas. This is small and forward scattering, back scattering is theta equal to pi. This this theta equal to pi by 2. So definitely there will be some theta dependence. But if it is spherically symmetric, it means that you have cylindrical symmetry. See, you already chosen this direction. Yeah. So complete spherical symmetry is broken by the choice of the incoming wave. However, cylindrical symmetry about that axis is still present because both the incoming state and the potential have that symmetry. Okay. So for spherically symmetric potential, f of theta phi is independent of phi. Okay. So it's only a function of theta. Yeah. See, at this point, this R doesn't mean anything. Okay, we have R to the power of 4 also. We are not discussing the precise behavior just yet. Okay, so, but in order to understand that better, we need to actually write down the equation.